Okay, so we are going to look at applications with derivatives. With these, we're going to be looking at that rate of change, both the average rate of change and the instantaneous rate of change. When we first started learning about derivatives, we found the average rate of change. We found the slope in between 2 points. So for instance, if I have this function and I want to find what my average rate of change is between these 2 points, I find, which makes up that secant line, I find the slope of it. So I find this coordinate point and this coordinate point, and then I do my change in y over change in x. However, then we learned with derivatives, we can find the instantaneous rate of change. So same function. Now I'm just finding the slope of the line that's tangent at that spot. So instead of needing those to be separated out. So if you want the instantaneous rate of change, as we did earlier, calculate the derivative at that specific value, versus if we want an average rate of change because it's not a linear function, then you just do your slope formula. So now we're going to get into some real world applications with it. So this is our cost equation for the specific problem. What we're going to do is we're going to find the derivative of it, which is the marginal cost function. So the marginal cost equation is when I take the derivative of this, and it has a special meaning. Now this equation is just specific to this scenario, but we'll have all different ones. Okay, so when we take the derivative, so when I take the derivative of c of x, so doing all of the multiplication, we should end up getting 0.00039 x squared plus multiply the 2 by the 0.002, and we get 0.004x, and then derivative of 5x is 5. So that's my derivative function. So now what I want to do is I want to find my marginal cost when 150 items are produced. So what that means is I want to plug 150 in for x in my derivative function, because again, this is the marginal cost function that we just found. Nope, nope, it's just the first derivative. I don't know. You were practicing derivatives. Okay, so plugging in the 150 in for x. So when we do that, we end up getting $14.38. Did you guys get that? Okay, so now comes the thinking. When I took the first derivative, so when I took the derivative of my cost, again, that cost equation is telling me how much it's going to cost me to make whatever my items are, okay, however many items I have. So X is the number of items that we're producing. So if I put 150 into the original problem, that would tell me how much it would cost me to make 150 items. But instead of plugging 150 into the original equation, into the cost equation, I put it into the marginal cost equation. So think about what the derivative does. When I take my derivative and plug a number into it, just any normal function, when I have a derivative and I put my value in, what does it instantly give me? Slope. Slope. It's growth at that instant. It's growth, what it's going up by. So therefore, what does $14.38 represent? That's okay that you're stumped. Of what? Yes. So to bring that full circle, let's calculate C of 151. So now we're going to go back to our original cost equation, and we're going to calculate C of 151, and we're going to calculate C of 150. And then we're going to subtract the two. So when you substitute in 151, check my math, but it should be $3,448.19. And when we purchased 150, or not purchased, produced 150, we got a cost of $3,433.75. And so when I subtract those two numbers, I end up getting $14.44, which is really close to B. because what B does is it tells me how much it will cost me to produce one more, because that's that growth. That's what's happening from one thing to the next. So this is approximately equal to C prime of 150. And that's what happens when you take the derivative of a cost equation. That gives you what's called the marginal cost equation or marginal cost function. Okay, next application. Looking at temperature for this one. During 1 month, the temperature of the water in a pond is modeled by the function T of n equals, where n is measured in days and capital T is measured in degrees Celsius. So A, find the average rate of change during the first 18 months, or 18 days of the month. So read them very carefully. This one asks for the average rate of change. Do I need to find the derivative for that? No. I'm literally finding the slope between 2 points, which means I have to know, and it says the first 18 days, I need to know T of 0 and I need to know T of 18. So use your calculator, go ahead and plug those in, and then we'll do our slope formula with it. So when I calculate T of 18, subtract T of 0 over 18, I end up getting, let's see, I'll do it over here, positive 0.0297 degrees Celsius. Is that right? Did you guys get that? Yeah. And then it's per day, because it's the slope, so it's temperature per day. Okay, B then says find the derivative. So when we take the derivative, and I'm just going to write it here because I have to slide down. So just bear with me for a second. So when I take the derivative of that function, what is going to happen here?
I forgot the name, but the multiplied one.
The product rule. Yeah. This is the product rule because there's a function here and this is a function as well. So you have to do the product rule with this piece when you take the derivative of T of n. So take a moment and go ahead and calculate the derivative for T of n. Okay, so the derivative of 18 is 0, so that goes away. So now I just have this to work with, the product part being these two individual pieces. So therefore, 12n times the derivative of e to the negative n minus 3, which is e to the negative n divided by 3. Chain on the derivative of the exponent. Derivative of the exponent is negative 1/3. Plus the second part times the derivative of the first part, which then just simplifies to negative 4n e to the negative n over 3 plus 12e to the negative n over, ooh, I put 2 before, sorry, that's a 3. Sorry about that. And then I want to find the exact value of the instantaneous rate of change. So always looking for which word it is they want. So instantaneous rate of change on day 18 means I need to calculate T prime of 18. So type this all into your calculator with the 18 in there. When you type that into your calculator, instantaneous rate of change is negative 0.149 degrees Celsius per day. So at 18 days, it is going down. The temperature is going down by 1.49 degrees Celsius per day. Versus if I look between day 0 and day 18, it was actually, the weather was actually going up. It was a positive growth. Because at some point it must have been more positive than it was negative, because again it was that average rate of change. Okay. Now we need to be able to check this in our calculator. So now when we check this in our calculator, what we have to do is we have to be able to put in our original equation into our calculator. So type in 18 Maybe if it'll let me. Be nice to your calculator. Plus 12 x e to the x, so second natural log, negative x over, over 3. Plus 12. And then I don't know what my window is going to look like, so I'm just going to change my window just for safety from negative 50 to 50 for both x's and y's. I just need to make sure it fits on here, otherwise it won't do it for me. It doesn't have to be anywhere near your function, just has to fit in your window. So don't take any time when you're making your window. Just put it in here and see what happens. Okay, don't even think about it. So there's the function from a negative 50 to 50 window. So now it wants us again to double check the instantaneous rate of change at day 18. So if you're on a calculator part of your test, your calculator does this for you. Second, trace, calculate dy dx, and then just type in your value, 18, enter. And there's your derivative value, which is what we had just calculated. So don't be afraid to use your graphing calculator. Now, if the problem was worth quite a few points, there might be more to it, and you would know whether or not you should or shouldn't use your calculator. Okay, but you're gonna most likely have to use your calculator anyway, so don't be afraid to use this feature on it. Okay. 7. So a diver jumps from a platform at time t equals 0 seconds. The distance of the diver above the water level at time 2 seconds is given by the following, where s is in meters. To find the average velocity of the diver during the dive. So average velocity. What do I need to calculate if I want the average velocity? Average rate of change. Average, so it's rate of change, average rate of change. So I'm going to calculate s of 0, s of something else, because I have to find between what values it is. It doesn't tell me though. The last problem said the average rate of change in the first 18 days. But this one just says over the length of the jump. How long was the jump in time? Do we know? So how do we calculate it if we need to find it? Set it equal to 0. I need to figure out when it hits the water, when this person hits the water. So set your equation equal to 0. I have to do that before I can even find my average velocity. Problem like this, you're going to use your calculator. So type this equation into your calculator, and it will give you 2 times, one of which is negative, one of which is positive. Let's just, for quickness sake, use the answer 2.0135. So you have to figure out where it equals 0, so you can put it into your calculator, put this into y equals, put this into y equals, and find where they intersect. Or you could do the quadratic formula if you really wanted to. So therefore, I have to find my average velocity, which is equivalent to finding s of 2.0135 minus s of 0, because we started at 0, and then dividing that by the difference of 2.0135 minus 0. So go ahead and calculate those. It shouldn't take you very long. What's s of 2.0135? 0. That's what we set it equal to. And s of 0, and I put 0 in, what do I get out? 10. So I'll go ahead and divide those 2 values. Okay, so we got negative 4.97 meters per second. That's his average velocity from the entire dive. So that's part A. But again, first thing, you had to figure out how long did it take that dive to happen. Part B then says find the velocity of the diver at the instant the diver hits the water. So now what we're looking at is finding how fast was he going right that instant he touched the water. So if I want to find that instant he touches the water, what do I have to calculate? The derivative. I have to find instantaneous rate of change. Therefore, I have to calculate S prime of t. And then once we find that, we want to find our instantaneous rate of change when our time hits the water, which is the 2.0135. So I'm now calculating S prime of 2.0135 because I want the instantaneous rate of change at that time. Negative 14.8 meters per second. And then part B says explain why the answer is negative. Well, the diver is moving downward, so that's the direction he's going in. Up would be positive, down would be downward. Normally, if we were looking at this velocity to the right of wherever we start is positive, to the left is usually negative. But in this case, we're just going up and down, so going up is positive, going down is negative. Okay, and then C, we just explained C. D, finding the speed. So these two look almost identical. The only difference is the word velocity versus speed. Last year's test had this exact same scenario on it. This is a really easy 1-point answer. Because you know B, whether it's right or wrong, what is your answer for D? The absolute value of it. Fantastic. So it is 14.8 meters per second. Speed is never negative. It's just the absolute value. Okay, so the second to last example, the cost per item in euros to produce X items is this cost equation. Find the number of items that must be produced to minimize the cost per item. So we are talking about a minimization problem, but I'm giving you the equation. So if I want to find what the minimized cost per item is going to be, what do I have to do to this equation? Find the derivative and do what with it? Set it equal to 0. And once I set it equal to 0, what am I going to do to it? Sign diagram. Yep. So take a couple of minutes, go ahead and answer that problem. Now be smart about your sign diagram. We're talking about items. So in my sign diagram, I have this value out here at -1. I cannot have -1 items. Therefore, it's really going to stop at 0. Okay. Now it doesn't matter because no matter what, it's going to be the same negativity through here. We're only looking at minimizing a cost. We don't have a bunch more zeros, so we do have to be careful if this kept going in one direction or the other. But when you do your sign diagram, between -1 and 3 or between 0 and 3, those values happen to be negative. These happen to be positive. If we really wanted to keep going, those are positive back there. But since we want to minimize the cost, minimize is a negative to a positive, which means it takes 3 items to minimize. I tried to fix it. I'm sorry. We'll just circle 3. Okay. Yeah, pretty much. Right. Okay, so the last one. Now this one is going to take some thinking. So if you're doing this at home, pause it right now and make sure that you're ready for this. You guys, just let's go. So we have a rectangle inscribed under the curve. So in other words, what that means is this rectangle touches this curve at both of those spots. So it physically touches there. And then we have these points C and D. So the coordinate B is x0. And the coordinates at C are x and then 2 cosine 1/2 x. Folks, I don't have to give you this. I do not have to tell you that. You should know it based on the problem. So because this is x here at B, at C, the horizontal length of that has to obviously be x as well because it's a straight vertical line. The y value of it comes from this equation over here. So since my input is x, that's my input x, I would substitute x with x. Oh, look at that. My y value, therefore, is 2 cosine of 1/2 x, which is what they told you here. So keep that in mind, as a lot of times they won't actually tell you this. You should know it because your input was X. Even if my input was 2X, then I should just put a 2X in place of this X. Okay, which would then make this X. It would simplify a little bit. But they shouldn't have to give you this coordinate point. You should know that. So based on that, we can then write expressions for our length AB and for our length BC. So our length of AB, okay, so we have our length AB. What does our length AB equal? 2X, because it's X on each side. And our length for BC, so from B to C, 2 cosine 1/2 X. Good. Because this is X and this is X. Okay. So part B then wants us to write an expression for the area. So we can now do our area. A of X, area, is length times width. Go ahead and simplify that. That 2 didn't need to be in parentheses there. It's just all multiplication. It's 2X times 2 times cosine of 1/2 X. So that's B. That's A of X. And then part C. C wants us to find the derivative. And what do you notice in here, guys? What are we going to have to do? Product rule. So go ahead and take the product rule of each of those 2 individual pieces. So I'll give you a few minutes to do that. So it's the second times the derivative of the first, plus the first times the derivative of the second. Don't forget to chain on the derivative of the inside. So therefore, when I simplify all that, I get 4 times the cosine of 1/2 X minus 2X sine of 1/2 X. And then for part D, it wants you to find the value of X where the area is maximized. So if I want to maximize the area, what do I have to do to this? Set it equal to 0. And folks, you are not going to do that by hand. You are absolutely going to use your calculator. So into your calculator, type y equals 0 and y equals this stuff. Make sure your calculator is in radian mode, please. So back to here. Because trying to find where it intersects with 0. Keeping in mind our scales from -50 to 50 again. However, it tells us in the original problem, X goes from -pi to pi. So I can change my window from -pi to pi. And then from here, I need to calculate where they intersect. And this is why I put in y equals 0. It's easier to just do an intersection than it is to do an x-intercept. Like if you do an x-intercept in your calculator, so let's go to that. So second trace, so if I use the calculator on here, I can do 0, but then I have to go to the left, to the right, etc. I just want to find where these two things intersect each other. So I just do 5. And let's move our cursor approximately where it is. Right now I'm on the blue curve, which is the straight line. Enter, it switches it. So I'm going to do both of them. I'm going to find each of these points of intersection. So I have one point of intersection at negative 1.72. Then I want my second point of intersection, same thing. Calculate intersect. Now I'll move my cursor closer to the other one. Enter, 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 and I get my other one. They just so happen to be symmetrical about the y-axis. So back here, what I calculated here were both of my values. So this is part E still. So the value at negative 1.72, etc. And then I have one at positive 1.72, what have you. I can use my sign diagram to find values, put the numbers in between, like put 0 in here. But fortunately, I already have that. So I know the values in between here are positive. They're above the x-axis. The values down here are negative, so I don't even have to plug numbers in. I can just do my sign diagram. It is nice when you already have it done. And therefore, since this goes positive slope, negative slope, there is your maximum value at 1.72. So now I can calculate my area. So when I type that in, 4.49, and again, I can use my calculator, and they're telling us to use our calculator for this. If I go back to my calculator, I can put my original function back into my area. Yep. And figure out what my values are. So let's just put it right on top. So it's 2 cosine. Oh, no, my area. Sorry. Yeah. 2x 2 cosine 0.5x graph. And there it is. Second trace, calculate a value. So again, I wanted to find it at 1.7, etc. So 1.72, enter. And you get that 4.49. You should, yeah, that way you have less round off error. Yeah, exactly. Do you guys feel comfortable using the second trace button? There's so much stuff up here. This is one of the things that I've struggled with trying to help students with IB, because so much that we do in our regular classes, we are like, no calculator, understand this, no calculator. So then all of a sudden when I'm like, hey, let's use our calculator, you don't always know when to use your calculator. So you're good at that? Okay, so your homework, 13D, 13E.